Come on.
No.
Oh my gosh. We should do
Okay.
it at this point.
Okay, guys, calm down. So let's get to the lecture. But before we start the discussion of the paper, I have to give the background. I have some feedback about your submission of reading note 2. So, as a general trend, I have observed some improvement the way you guys are writing the summaries and trying to identify the weaknesses and strength. Like, for example, in the first submission of the reading note, it was like you were complaining more about, many students were complaining about, okay, the writing style or this thing was not clear or something like that. But in the second, it was more about on the technical side, and which is a good sign. Summary also, as I gave you the feedback after the first reading note, that in the summary, you focus more on the general idea, the problem which is addressed, the solution which is proposed, the contributions which are made, the challenges which are faced by the authors, and you focus less on weaknesses on the strength. And I have seen more students following that guidelines in the reading note too, which is good. But one thing which I again want to highlight, which was like mistake in reading notes 1, and I also observed in reading note 2, is like students are complaining, like some students are complaining, and I understand why you are saying that, but like, for example, there is too much information, which are too many topics or concepts we are not aware of, and we would like authors to have explained it in a little bit more detail. Or some people are like, in the related work section, they have given pointers or links to the other work, but without explaining them in detail. But that is typical of the research paper, because they are already condensed. And that's why, and on the top of that, they assume that the people who are reading, they are aware of many of the related work, if not all of that, but at least the readers know, or at least they have the skills to go to those papers and at least read the abstract, or if they don't know it in advance, the introduction at least. So it is typical. So you cannot count it as a weakness of the paper. So for like reading note 3, don't list as this aspect as a weakness. Or similarly, like, let's say they have not given enough detail about something. For example, here they have in this paper, they have a subsection in the background about page sharing, right? But let's say they don't talk about it in detail about, let's say, about TLBs. So you cannot count it as a weakness, because it is assumed as a common knowledge. Okay, so focus more on the technical side of the paper. And if you don't know something, try to. That is what I also am doing, to use ChatGPT to understand that there are some things which you don't know, because ChatGPT is good like at giving you a right amount of details. Like, first, if you ask a question, it gives you like a higher level answer for that, and then it can ask, do you want me to go deeper? You can dig deeper and deeper until you are satisfied. Okay, so flush plus reload. So this is our third paper we are discussing, and our first paper was totally a survey paper. Second was, I would not count it as a survey paper, but it was exposing the vulnerabilities, but it was not a concrete attack, in the sense that yes, they have identified the vulnerabilities, but then they have not used the vulnerabilities to launch an attack. But here, this is the first paper where they are exploiting a side channel to launch an attack, actual attack. Okay, so how many of you have read the paper? You are presenting, right, Javier? Who's presenting? Who's discussion lead? You. Okay. So I want you to be more active today. You ask more questions and try to respond to as many answers, as many questions as you can. Okay. Okay. So What's the motivation? I mean, this is an attack problem. Normally, when we talk about the motivation, the thing is like there is an existing problem and this problem is important to solve. And if we don't solve this problem, then these are the implications which we need to face. So that's why we are going to propose this solution. But this is an attack problem. So here we are saying, okay, we are going to create a problem. So the motivation is like there were already some existing cache side channel attacks, but they had some weaknesses, the existing attacks, which were like, okay, there will be some terms you are not aware of. If not, let me know. And I have a plan to discuss them in the upcoming background slides. Okay. So in the existing cache side channel attacks, the weaknesses were like they need the spy and victim processes to share the code, which reduces the spy's flexibility. So in modern processors, what happens is that let's say you have this chip, and on the chip you have multiple cores, right? I'm not trying like let's say let's make it 4 to keep it even number. Okay. And what happens that inside each core, every core has its own L1 cache, both data and instructions. So the caches are inside the core and they are private to the cores, right? And then L2 is also typically private. But then L3, which is also sometimes named as launch level cache. So this is shared among all the cores. And then this is connected with the memory, which is on a different chip. So this is like memory chip, okay? So here what they are saying is that the previous attacks which were exploiting the cache side channel, what they wanted the processor, the spy process, which is launching the attack, and the victim process, both to share the same core, which basically mean like, remember in the previous topic we talked about like, if you have a dual issue, if you have a dual issue process, you can a processor, you can issue 2 instructions at the same time, right? So what happens like actually in one single core, you can support 2 threads at a time, 2 virtual threads at a time, okay? 2 hardware threads. So what they want is like they want both the process, the spy process and the victim process to be running on the same core. So if they are running on the same core, then they are putting their data in the first level cache, L1D. Okay, and those attacks for exploiting the L1D for launching the attack. But the problem with this is like this kind of approach is like if your spy and victim, they are not running on the same core, but on the different cores of the same chip, same processor chip, then the previous attacks, they will not work. So that was the problem. Okay. And definitely this kind of an attack will also not work in the case where you have virtual machines, multiple virtual machines running on the same host. Okay. So the existing attacks, because the existing attack was exploiting the L1 cache. So if you have multiple virtual machines, so they are also running on different cores. So if they are running on different cores, they are not sharing. So as a result, if there is no sharing, there is no leakage of information, and then you cannot exploit that leakage of information to launch that. Okay. So as a result, just spy's flexibility reduces. Also, the problem was that they identify accesses to the cache set. I will explain what is cache set later on, but the thing is like a cache set contains within it cache lines. So in one set, you can have multiple lines. So you identify that, okay, the victim is accessing which particular cache set, but you cannot identify which particular cache line inside within the cache set. So as a result, what happens is that, yes, you have information, but not fine-grained information. So as a result, which means that you need to do extra processing to figure out what is the access pattern of the victim. And they also have false negatives. I will explain later what is false negative, okay? And it may not work in presence of ASLR. ASLR, again, I'm just taking note here. So if I forget to explain when I'm explaining the paging, if I forget to explain the ASLR at that time, let me know. So it stands for address space layout randomization. Address space layout randomization. Okay, and it is a defense mechanism against security attacks. So the existing attacks, they would not work if the ASLR is enabled. Okay. So then here what they do is like they exploit the cache side channel for an attack that is free of all those weaknesses, right? Definitely it has its own weaknesses. So it does not need the spy and victim to share the same core. So as long as the spy and victim are running on the same processor, their attack will succeed. They don't require the spy and victim to be on the same core. If they are on the same core, well and good. If not, but on different cores, still the attack will work. Because they use LLC as a side channel, not the L1 data cache or L1 instruction cache as a side channel. They do not suffer from false positives. Again, I will explain later what is false positive, but they don't have false positives, which is a good thing. And they have high resolution, which basically mean that unlike the previous attacks, what they are doing is they are able to identify the access of a victim to a particular cache line, not only to a particular cache set, but what particular cache line within a set. So which is like, it gives you more information and more control. And it can also work in presence of ASLR. And it can work when your spy and your victim process, they are running on the same OS, or even when your spy is a one virtual machine running on one virtual machine, but your victim is running on a different virtual machine. Okay.
So just real quick, when you say good thing, is that referring to us as an attacker or as the defenders? Like, when you say it's a good thing, it doesn't have from false positive, that's because as the
in this
attacker, that's
context,
good.
in this context as an attacker. Okay. In the context of this attack, it is good for me to not have false positives. Okay. Okay. So here they are assuming that spy and victim, they share the memory pages. So what is like how memory pages are shared and in what scenarios we share them, we will talk about them, but they are making this assumption, which basically means that if this assumption is not true, then this attack will not work, which is like a weakness of this attack mechanism. Okay, so their idea is that they use the last level cache, LLC, as a tool to identify the memory accesses of the victim. And then the spy times its own memory accesses to determine if a cache line was accessed by the victim or not. Any questions, comments? Okay, so this is like the basic idea without going into details at a high level. So let's first look at the victim, first figure. In the first figure, we have victim and attacker, and let's first look at the legions. So the blue are, how many of you know what is flush and how it works?
Clears the memory line.
Yes.
Like the no operations you mentioned from the last class?
Yeah, no operation clears your stages of the pipeline, but flush is.
But it was pushing the memory to the LLC from the core.
So say it again.
So from L1, L2, it's all getting sent to the LLC. So it's like affecting it.
No, not to LLC, to the memory.
Okay, so the main memory, so it's
Yeah.
pulling it from the.
It
LLC
removes the data, your cache line, from all levels of your cache hierarchy. L1, L2, L3, LLC, whatever it is. And it puts the data in the main memory. Okay. So this blue color indicates the flush operation. This is gray is wait. And so flush is when actually you can execute an instruction CL flush. So whatever, let's say if I execute the CL flush, what I need to specify the address as a part of that instruction. So which basically I'm by executing that instruction, I'm telling that the cache line, which corresponds to this particular address, evict that cache line from all levels of the cache hierarchy and write it down into the memory. Okay, so which means that if I flush it and you are also using the same, that's it. This is the spy running here, and this is the victim running here. So what they are doing is that, what does the spy do is that the general approach, that spy will first, and basic assumption is that they both of them are accessing the same memory address. I will go to we'll address that in more detail later, but for now, let's say we assume that both are accessing the same physical address. So what does the spy do is that initially it flushes a target address, the address which it knows in advance, somehow it knows that this address is accessed by the victim. So it flushes it. So for flushing, you can use this instruction CL flush, and then you provide the address as a part of this instruction, okay? So what will it do is that the cache line which corresponds to this address, it will be flushed from your cache. If let's say you had a copy here, that copy will be removed from here. It will also be removed from here, and it will be the latest data, latest version of that data will be written into the memory. So flushing means that remove from here, and written down to memory. Okay, so then wait is after that, what does the attacker do? The spy waits for the victim for some given amount of time or some predetermined number of cycles. And for the waits, and then it assumes that victim will perform an access to the same address. But this is again an assumption. We don't know whether for sure whether the victim will do the perform the access or not in that within that wait period. So if the victim, and then after that, your attacker comes back and it tries to read the same cache line, which it had flushed. It knows the address, right? Because it had flushed using the same address. So it tries to read the data from the same address. If the data is in the L1 cache, which you can check or test by looking at the latency, how long it took for the spy to get the data. So if it takes less time, it means the data was already there, which means, or at least not here, but here in LLC. Because if it takes less time, then it's mean that the data was placed at LLC by the victim. So it's mean that while I was waiting, victim accessed the same address. But if it takes relatively longer for me to access the data, it's mean that while I was waiting, victim didn't access the data, the same address. Okay. So here there are different scenarios. So this was like the basic approach, and here they have different scenarios where in the figure A you have victim and attacker. So what does the attacker do is first flushes the address, then it waits for this amount of time, and then it tries to read the address. So when it tries to read the address, it sees a longer reload time. It tries to reload the same address. So it sees that it takes longer amount of time for that reload instruction to complete, which basically means that victim has not accessed the data while the attacker was waiting, right? Between the flush point and the reload point. Second is where the victim accesses the data between the flush point and the point where the attacker reloads. So here the victim accesses that block. After that, when attacker reads, it still sees like latency of reading the data, but this latency is much lower than this one, right? Why? The reason we already have talked about that, because the data, when the victim is reading it, it places a copy of it in the LLC. I will come back to this later. Okay, this is the third scenario where between the where attacker flushes, waits, and then when it tries to reload the data, at the same time, victim is also trying to access the same cache line, same address. So, but the access of both victim and attacker completely overlap. which basically means that attacker first issued the request, and while its request was being served, a request arrived from the victim also for the same address, which basically means that victim has not already placed the copy of the data in the LLC, and as a result, victim attacker sees the longer latency of accessing the data because there was no copy already available.
So just like the producer consumer issue, where the consumer tries to consume the product before the producer.
Something similar to that, but there is a difference between there is a difference in the context, in the sense that in the producer and consumer case, both are cooperative processes. Cooperative processes mean that they are using the memory to exchange the communication. Okay, but here the address is shared not for the purpose of communication, but for the purpose of reducing the footprint of individual processes. Let me answer it right now because I know then you will keep thinking about it. Yeah. So, okay. Actually, I have all that in my list, but maybe I don't need to follow exactly the same order of the things. So, okay, that after I have explained this, remind me that I need to go back to the figures. Okay. Okay. So, here is the issue. For those who have taken the operating system course, you may know it already, that we have the memory on the memory chip, right? The physical memory on the memory chip. But doesn't matter how large it is, what is the size of the memory, at the end of the day, it is finite, right? So let's say I'm just giving an example. Let's say you have 10 gigabyte of memory, and there is a process which you have two processes. Both of them need 10 gigabyte of memory to run. So it's not possible for you to run both the processes at the same time, even if you have multiple cores, right? You can say I have multiple core, I can run process here and the other process here, but both of them need 10 gigabyte of the memory for their execution. So it's mean you cannot run both of them at the same time. So what does people do is, like the original approach was approach in the old time was like, let's say you have this 10 gigabyte of memory and you allocate all of this to the process A. Now only process A can run. Once process A is done, or you kick it out, so then you put it into sleep something where process B doesn't need the memory anymore, then you can use the process B. Let's say process A is done, it's terminated. Then you can use the process B and run the process B and allocate it all 10 gigabyte of memory. But definitely this will slow down your system significantly because you cannot run more than one process at a time. So what that people do is okay, what I can do is so you know that memory is volatile, right? I mean, in traditional systems, it is volatile. And what you do is that you put your data in the disk for durability, so that your data is not lost. So data is actually moved, whatever you have, file or data, code or data, whatever. Everything is moved from disk into the memory, and then from memory, you move it into the processor for execution. You read, load, store, right? Okay, so to solve the problem, people say, okay, what we can do is like instead of giving or allocating all 10 gigabyte memory to the process A, what I can do is I can divide my memory into chunks. Okay, in physical memory. This is physical memory. Okay, and each chunk is named as a frame. Okay, then there is something which is named as virtual address space. So what is virtual address space? So let's say if you have a 32-bit system. So if you have a maybe you have seen like Intel 32-bit, Intel 64-bit, right? What does it mean? It means that if you're using Intel 32 bits, mean that it has 32-bit address space, which basically mean that the address bus has 32 bits. So if address bus has 32 bits, it means like how many total number of addresses you have. Like if you have 2 bits, how many total number of addresses you can make out of 2 bits? 4, which is equal to 2 raised to power 2, right? So if you have 32 bits, you can make 2 raised to power 32. And if you have 64, then 2 raised to power 64. So all this, the collection of all these addresses, let's say I say 2 raised to power 32, collection of all these addresses makes the address space, like starting from 000 to all ones, FFFF, okay? So that is called the virtual address space. And the virtual address space can be much bigger than the physical address space. Like let's say your processor is using 64 bits, so your total virtual address space, which is available to each process, which basically means that each process can generate addresses in any range from 00 to all ones. And there are 64 ones, which is a huge number, right? Now, how much it is, like 10, 20, I don't know, I mean 10 is kilo, then another 10, 2 raised to power 10 is kilo, 20 is mega, and you can go on, I don't know, I mean, this will be a big number, more than gigabyte, right? But your chip is not that big. So basically what happened is that your virtual address range is much larger than your physical address space. So maybe physical address space is, let's say, only 10 megabyte. But your virtual address space is, let's say, 10 gigabyte, okay? So the addresses which are generated by a process when it is running, they are within the range of that maximum range, like all zeros to all one, okay? And that is called as virtual address space. Now, what would we do is like, now I'm removing it, erasing it, so you got it already, the idea. So now let's say this is your virtual address. This was physical address space, okay? Physical memory, this is your virtual address space, or VA, okay? Starting from all zeros, I don't know how many, depending upon your number of bits, all ones, okay? So what they do is like, you break it also into the equal size chunks. Each chunk has the same size. And these are known as pages, okay? And the size of the page, so page is a notation or a term you use for virtual addresses in the virtual domain, and frame is like physical memory, okay? But both of them have the same size. So typically, this is 4 kilobyte, and this is also 4 kilobytes, okay? Now what happens is, so every process has its own virtual address space. Like let's say this is process A. Then similarly, a process B will have its own virtual address space. Then what you do is you put a table in between, which you name as page table. And every process has its own page table. So let's say this is page table B, and this is page table A. Okay. So it will tell me that, okay, I will give you a virtual address. So let's say the virtual address generated by the virtual address is generated in this virtual address space by the process. And let's say this is only address X. So this table is indexed using the virtual address. Let's say this is the value. If you want me, I can give you like a concrete number, like let's say 1024. So I will go to the table at the entry number 1024. And then the content of this entry will give me the physical address, physical address of the frame. So basically, if I want to access any data, so any data in this page, so I first need to translate this virtual address into the physical address. How I know, how I get that physical address? I look into the page table of process A, go to the given address, look into the entry. This entry gives me the physical address. This physical address will point to some frame, which is like the location in the memory itself. Okay, getting too bored? I mean, Are you with me or like, okay, if you have a question, ask. Because if when everyone is silent, it is like I'm talking to myself, yes.
So then the whole point of the DAC is that there are two,
The whole point of what? Whole point
of
of?
the DAC is that there are some processes sharing the same page.
Yes,
On the virtual
yes,
address
yes.
space.
Yes, yes. Now I'm coming back to the question. Like this page, this process will have its own page table. Now, maybe you have heard about the shared libraries. Like, for example, let's say you are running a C program. You have two different C programs, or both are using math library, which implements like different functions. Let's say square root function, right? So one thing is like one process or one program, it has its own in the physical memory, in the same physical memory. Let me just break it. Let's say, I can keep it. Let's say this has its own copy of square root function, like the code. And then the process B, so it has its own entry, like here you have virtual address, which gives you the physical address, and you go to a different physical address. You are wasting memory, right? Because the same library is used by two different programs, and you are keeping two different copies. And now assume like multiple applications are using the same math library. See, multiple C applications or programs are running, right? So what you do is like, what you can do is like, you can have the page table of process B. The virtual address may be different, generated by the process B, and the virtual address generated by process A, maybe they are different. But by looking at the page table, they both point to the same frame. Okay, so in this way, you don't need to have multiple copies, and you reduce the footprint, memory footprint of the processes, because you are sharing the libraries. Now, just assume that process B is victim, process A is spy. And this library is not square root library, it is like RSA encryption, decryption algorithm. Okay. So, yeah, so they assume that the pages are shared, and if the pages are not shared, then this attack will not work, right? So in C, what they are doing is, okay, I talked about it already. There was overlap. Because of the overlap, but the attacker first sent it request, so it still sees the longer time. But the problem here is that yes, the victim is doing the access. Access is overlapping. That's why attacker fails to detect the access by the victim, because both are overlapped. Attacker is successful to identify the access by the victim only when it is performed before the reload operation. Okay, or it can also create a difference here where victim first starts the request, and while it is in progress, then attacker sends the reload. So because it is already in progress, so attacker sees relatively lesser amount of reload latency, lesser as compared to this one, but more than as compared to this case where victim has already completely loaded the cache line. Okay.
So if they overlap during the reload, does the attacker still get the information, or is it lost in the attacker's view?
Okay. Anyone who want to answer? That is a good trick when as an instructor I don't know the answer. So if you read the paper, that their basic tool is that they are building their attack on identifying the excesses.
Yeah.
And how they are identifying the excesses? By measuring the latency observed by the attacker. So here the latency observed by the attacker is same as to this case, right? Where victim didn't make an access.
Yeah.
Here, although the victim is making the access, but at the same time, and as a result, they see the larger latency. So the attacker fails to find out because its measure is the time latency. So it cannot find that, it thinks that the victim has not made the access, while actually the victim has made the access. But at the same time. Yeah.
So in this graph, you're just probing for latency, not necessarily probing to find that same address that the page is in, right?
Yeah, that's a good question. So maybe if I'm rephrasing your question, but if you think I have distorted it, let me know. So are you asking like how, as an attacker, how do I know what is the required, the correct address which I need to look at?
Yeah, I guess more simplified than that, in this view right here, this visualization, it's just testing for the probing if.
Yes.
if it's late.
Here we are assuming that we are already guaranteed we know the attacker has the correct address, it knows. Okay.
Gotcha.
Given that there are different scenarios where you know the address, but still there will be cases where you will be able to detect the access by the victim, and then there will be cases where you will not be. So ideal case will be where victim makes the access before my reload operation as an attacker. And then this is the last scenario where victim loads the target address multiple times between the flush step and the reload step. And in that case, also the victim attacker is able to detect it because it sees the lower latency. It doesn't matter whether you make one request or multiple, as long as the victim leaves the data in LLC, a copy in LLC, as an attacker, I will see the lower latency. Okay. Okay, so how many of you, okay, anyone who knows the answer, raise hand. What is an inclusive cache? What is an exclusive cache? No. So this attack works only if your cache is inclusive. What is inclusive? I will explain. But that is like kind of a weakness of the. So it works when your LLC is inclusive, and your processes, spy and victim, they are sharing the pages. If any one of them is not true, these conditions are not true, the attack will not work. Okay. Okay. I can erase all that, right? Okay. So I want to explain it here because then it will make sense for you, like, to understand why this attack works only when caches are inclusive. So what are inclusive caches? So let's say you have 3 levels of caches. L1, L2, L3, which is also known as last level cache typically. And these are private to a core, and these are shared among the LLC is shared. So inclusive cache is one where if you have, and by the way, before I go there, so this one is known as lower level, though I think it is counterintuitive, and this one is known as higher level. But anyway, I don't know, maybe this is some terminology left from like history, but that is how they are naming it. These are lower level caches and this is higher, although these are closer to the core. Okay. So inclusive cache is one, like if you have a data or a data block in the L1, it is guaranteed you have the copy of same block in L2 and L3. Okay. I'm repeating again. Inclusive is if you have a data block in L1, you are guaranteed to have the copy of the same data block in L2 and L3. Okay, and all are latest copies, not stale copies. Okay. If I state it in a different way, so the same statement actually implies that if I evict a block from L3, its copies from L1 and L2 must also be evicted. You got it? So inclusive means that it has its copies on all the cache, or if it is like at lower level, data is at a lower level, then all the higher levels also have the copy of that block. And if the data block is evicted or removed from a higher level, then it also need to be evicted from all the lower levels. Yes.
So you could, try and like flush data from L3 that doesn't exist in L2 and L1 because it's the higher level, so there.
So
might
say
be-
again, say again.
Yeah, so since you said the lowest level has its data like replicated in the higher levels, or the other way around, so L1 has its data replicated.
Yeah, I
in
don't
L2.
use these terms because they are confusing for me, okay?
And then if L3 has data, it might not necessarily be in L1 or L2, it could be like its own data. So if you were to remove that, it might not.
Yeah,
have that
yeah,
effect
yeah,
on-
yeah. It is possible that you have a data block in L3, but it is not in L1 and L2. But if the data is in L1, it is guaranteed that it has its copy in L2 and L3. Because data moves from memory to this direction, okay? So, but and when the data is, let's say there is a data copy here and you evict its copy from L3, you must evict it also from L1 and L2 to keep the definition of inclusive caches, to apply the behavior of the inclusive caches, right? Because if you are evicting it from here, then and the data is in L1 and L2 but not in L3, then it is not inclusive cache anymore, right? Right? So that's why you need to remove. But then what is wrong with this approach? Okay, first tell me what is the good thing about this?
If the data block gets removed from L1 or L2, you can still access it from one of the other caches without having to go to memory. Right, it's just the same time.
That's good. Yeah, that's a positive point. Okay, there is another positive, but in the context of multi-core processing, let's not go there because then we don't have enough time to. Because actually, it will be easier to maintain the cache coherency in multi-core platforms if you have inclusive caches. Okay. Opposite to this is exclusive caches. Exclusive caches where but another disadvantage is definitely you are copying the duplicates, so you are wasting the memory space, right? So the opposite to this is exclusive. Exclusive is like if you have the data copy here, you will not have it in any other hierarchy, in any other level of the hierarchy. Okay. If data is in L1, it will not be in L2 and L3. If it is in L3, it will not be in L1 and L2. You maintain one copy. So that is like true definition. Okay. So now you understand why this stack will work only in LLC if LLC is inclusive. If it is exclusive, let's say, right? Then let's say your SPY is running on this core and it has its data copy only in L1. And victim is running on the other core and it has its own data only in L1, right? But the attack focuses on LLC. So if victim is taking its data to L1, it will not leave behind a footprint. It will not leave behind its data. So the attack will not be able to work anymore because attack works on the LLC. Okay. Okay, what are virtual and physical addresses? I have tried to explain it in a very quick way. Why are two different addresses needed? Basically to give an illusion to the processes that, to give an illusion to each process that whole address space, virtual address space is available to it, while actually this is not the case, and allow multiple processes to run at the same time. How they are translated to physical, virtual address is translated to physical address using page table. And every process has its own page table. It is not like you have one page table serving all the virtual to physical address translation for all processes. No. And how page sharing work, I gave you an example here using the square root example. Okay, what is typical cache hierarchy in modern processors? I think we have already discussed, but maybe it is a much more cleaner figure. So you have, let's say, 4 cores, L1, L2. They are separate in the sense that you have a separate L1 for storing the instructions and for caching the instructions, and separate L1 for caching the data. And L2 is unified, which means both instructions and it holds both instructions and the data, rather than the L1 and L2. Both L1 and L2 are private to a core. And then L3, it is unified and shared among all the processes. So all the cores, sorry, not all the processes, all the cores. So all the cores, L2s of all the cores gets the data from L3. Yes.
So L1 split into two things, is that purely just for like efficiency, or is there a security aspect for that as well?
Okay. I don't know what are security implications or security reasoning, or if even there is security reasoning for that, but yes, performance is definitely a reason for splitting the L1. Anyone who want to answer how splitting L1 improves the performance as compared to the case where we do not split the L1 into data and instruction cache.
Quicker access to its own L1 on each core.
But everyone has its own L1 anyway. Let's say even if it is not split, still every core has its own L1. So you have the case where let's say in case one, you have a core which has only unified unseparated L1, which stores both instruction and the data. And in another case, you have a core which splits the L1 into instruction and data L1. So how it affects the performance of, let's say, program or a process running on that core.
L2, would that mean that you'd have to in real time split the two apart? You'd have to process the different instruction and the data.
Yeah, so it's mean that at the same time, you can read instruction and the data at the same time, right? If you have, let's say, only one L1 holding both instruction and data, you can at a given time, you can read only instruction, or you can read data, right? So when you split, so you can allow at a given time to read operations to be performed on both. So if now you think in terms of like, if you keep the pipeline stages in your mind, so when one instruction is in the decode stage, or memory access stage, another instruction is in the fetch stage. In the fetch stage, that instruction is reading the L1 instruction cache. And the instruction which is in the memory stage is accessing the L1 data cache. Okay, so if let's say they were not splitted, then there is a dependency. If the instruction in the memory stage is reading from L1, then the instruction in the fetch stage cannot proceed. You cannot fetch an instruction, and you must wait for that instruction which is in the memory stage to complete.
It's like multi-threading.
No, it's not multi-threading, it is pipelining.
Okay.
Yeah.
Wouldn't that affect more of the attacker than it would the victim, or would it affect more of the victim than it would the attacker? Like thinking about it, if they were combined, it was a combined L1 and not a split L1. Does that make sense? Since it's more efficient.
In terms of performance, it will affect the performance of both any process which is running. It is not because we don't know in advance like which process is a victim and which process is a spy, right? Let's say you are running your program and I'm also running my program on the same processor, and I have malicious intent that it makes me the spy process, and maybe I can target any one of you. So any one of you want the process who I target will become the victim. So, but the efficiency, both the process, the spy and the victim, both of them get the efficiency benefit as a result of the split L1 cache. It has no way to figure out which process is of spy and which process is of victim. Okay, so I have explained how CL flush instruction works. There are two other variants of the CL flush instruction, CL flush opt, which means optimize, and CLWB, which is cache line write back. So CL flush, the issue with the CL flush opt is, let's say I have my program and I have some bunch of instructions and then I have CL flush and I give an address and then I have some other instructions. So these following instructions, they cannot execute until the CL flush instruction has completed, which basically mean until the data which I'm saying flush that data has been written down into the memory. So if let's say the data is copied from L1, L2, L3 to memory, it is evicted from here and written down into the memory. So memory is a different chip. And remember, I said whenever you cross the chip boundary, it takes more time for the data to travel. So it will take time for the CL flush to write the data here, and all these instructions will be blocked. Will mean they will be waiting first for this CL flush address to complete, only then they can execute, which will slow down your execution of the program, right? Even if they don't have any dependency on this address. Okay. So CL flush opt is like, it does exactly the same thing as CS flush, but the only thing is that it doesn't block the subsequent instructions. It allows them to continue if they don't have any dependency on CL flush or on this address. Okay. Let's say these instructions, let's say if this instruction is like load from the same address, then it will wait. But if it is like say add R1, R2, R3, no dependency they can do. Okay. CL cache line write back. It is another variant which is used in persistent memory design cases, where what you do is that you want your data block to be written down into the memory, but you don't want it to be evicted from cache hierarchy. So your cache blocks, your data still stays here, but only it is updated down in the memory. Okay. So actually what happens, because frequently let's say a process is accessing the data from here. So I'm frequently reading, writing it. Maybe I have an latest copy here, but the copy in the memory is stale, and then I need to update it. So I will say CLW, cache line write back, but don't flush it. That's why it doesn't have flush name in it. Okay. Okay, what is copy on write? Anyone who knows? Copy on write. Okay, so here I gave you an example that two processes are sharing a library routine, scale root, let's say. But scale root is the code, right? There can be cases where you share the data pages, okay? Like share between process A and process B. Let me draw the same figure again, but in a simplified form. Process A, process B, and it has a page frame in memory which is shared between both of them, right? Let's say some shared frame, okay? Now, if it is shared, and if process A wants to write the data in this page, it can create problem for the process B. For example, it can create the data consistency problems, or let's say, at the same time, when process A is writing a particular address, exactly at the same time, process B want to read that address. Or process B also want to update that address, but with a different value. Then how we are going to handle it? So what they do is that when they share the pages, the solution is you share the pages with a read-only permission. Read-only. Both can only read from that data, but cannot write. But whenever one of them wants to write, a page fault happens. I'm not going to explain it because we need to focus on the paper and we don't have enough time to go and explain the OS course related things. But just to make it simple, it happened that since it has only the read-only permission, both of them, And if one of them want to write the or update the data, so it doesn't have the permission, so it triggers the operating system. So operating system will, so it tells the operating system that there is a fault. So this is named as page fault, and then operating system will trigger a routine which will take care of the page fault, which is known as page fault service routine. Okay, which will explain, which will take care of how to handle the situation.
Is this similar to mutexes and semaphores?
No, mutex and semaphores, they allow you to synchronize the access. So synchronizing the access is like where both of them have permission to write, but we need to, let's say, enforce the ordering that, okay, page A can write only after page B, or we don't want to enforce the ordering, but we want to say that only one of them, doesn't matter in what order, but only one of them I can write at a given time. But here they don't have the permission. They have to write the data, only they can read. So what you do is like then the mechanism is copy on write, where what you do is that when there is a write request, the operating system creates a copy of this page, copies everything from this page to the new copy, and then allows or redirects the write request coming from process B instead of to the older page. Let's say I'm naming as page 1, redirects to the page 2. So as a result, what happens is that this can still, now it has its own copy of the data. And from now, this point onwards, any read requests or write requests coming from process B, they will be directed to the process 2, to the page 2. Okay, so this is copy on write. And this is like when you share the pages, there is a situation where you initially share the pages with the read-only permission. And as the need arises, as the requests arrive, you do the copy on write mechanism. Okay, we have 15 minutes, 5 minutes more. So what is temporal and spatial locality?
Is this referring to locality in memory? Like if you have,
It can be in context of both memory and caches.
like if you have two processes trying to access the same data, is like how close that data is spatially? That's what I'm assuming.
No, in context of caches.
Okay.
So what is the job of why we have caches? To reduce the time seen by a processor trying to read the memory location. So every time if you go down to the memory, it will take longer. So what we do is we make a copy of the data in the L1, right? So let's say the data you accessed was A, right? And let's say your program is processing an array of data, which is in memory. I'm not drawing here, but it is in memory, okay? A, B, C, D, E, so on. Definitely you can index it like these are addresses 0, 1, 2, 3, right? So you first time when you access A, you bring the data, right? And now you need to access the next element, but next element is not in the cache. So you go down again and bring the B. Right after that, you need to access C, which is not in the cache. Go again and bring C. So there is no advantage of cache in this case, right? So what you can do is like, you can look at the access pattern and then you can say, okay, what I can do is that when I bring the A, I can also bring C, D, B, C, and D. So first time I will go down to the memory to read A, but for the B, I don't need to go down to the memory because B was already copied here. Okay, so spatial locality, this is like spatial locality, which basically says that if a data element is accessed, then there is a probability that data elements adjacent to it in the memory will also be accessed in the future by the same program. So we anticipate it, and what we do is we'll bring them in advance to the cache. So this is like spatial locality. And temporal locality is where the data you have accessed now, you assume, or depending upon the access pattern, you think that it will be, same data will be accessed again in the future. So an example is like, while, let's say I'm making an infinite loop, just to give you example. Even you can make like some, like, let's say you can say count is equal to 10 while count, okay? And you can say, okay, a plus plus, okay? So, and then you decrement count. So in every iteration, you are accessing A and C, A, C, A, C, A, C. So here what you are saying is temporal locality is that the data which is accessed now will be accessed again in the near future. So we keep it in the cache, we don't throw it out. Okay, to improve the performance. What?
So even if you try to flush it, it'll still.
No, it has nothing to do with the flash. This is like temporal locality and spatial locality are like how you can benefit from caches depending upon the access pattern. But if even like, let's say you are saying, okay, bring B, C, and D also when you are bringing the A, but if you say CL flush, it will flush it. Okay, all of that will go down to the memory and evicted from the caches. Okay, I am skipping this part because these are like relatively kind of easier things. I want to go here because, especially for you. So, what is RSA algorithm? I have never worked in cryptography. I haven't taken any course on the cryptography. So before reading this, I also didn't know that. Just a disclaimer. So it is a algorithm using which you can encrypt the data. And let's say I am a sender. So I am supposed to have a public key. Using that public key, I can encrypt my data. And you are, let's say, receiver. You will have the private key. I will send you the encrypted data, which I encrypted using that public key, but you have your private key, and using that, you can decrypt the data. Now, if you don't have that private key, you cannot decrypt it, okay? And if now I'm an attacker, let's say between sender and receiver, there is an attacker. Now, if attacker figures out the decryption key, okay, then we assume that the attacker has access to the messages, but the attacker doesn't have the decryption key. So if you don't have decryption key, you cannot read my messages. But if you somehow you can have the you can find out, discover, or break the decryption key, you can read my messages, right? Okay, so in this paper, they are breaking the RSA encryption algorithm. Basically, what they are doing is that by using this flush and reload approach, they are figuring out the decryption key of the victim process, okay? Now, to explain that, maybe we can delay the reading note submission 5 minutes. You can maybe 10 minutes, so let me complete this, okay? Because that is important. So, here, what you do is like, if let's say you have a, okay, let me start from here. Let's say you have a message N, okay? And you are the sender. So you will encrypt that message first. So this is the encryption message, EM, encryption function. And how you encrypt it, you calculate the exponent of message to the raised to power E. What is E? I will come back to it. And then you take a modulus of that with N. Whatever, and you keep, after this operation, whatever you will get is your encrypted message, okay? And you will send that encrypted message. On the receiver side, I'm the receiver. So if I receive your message and I want to read it, I first have to decrypt it. For decryption, this is the function here. And C is your ciphertext, okay? M was like plain message, and C is cipher, encrypted text, encrypted message. And D is the private key. So I need to know D in order to decrypt it. And after taking like the exponent c raised to power d, then I take modulus operation with them. Okay. Now, what is n? So what you do is that you randomly select only two prime numbers, p and q, and then n is the product of p and q. Okay. And this public exponent e, it is known. It is like, let's say if there are multiple senders, all of you are sending data to me. All of you will need to have the same public key, right? So it is like publicly available. It is known. Okay. So because you need it in your encryption operation here. Stop me if you have a question, okay? And how the private exponent, this one d, is calculated? It is inverse of phi and then modulus of p minus 1 times q minus 1. So I need to, if I let's say if I'm a attacker, I need to figure out d so that I can decrypt the messages. Okay. Everything clear here? Okay. So the issue is like the way they have implemented RSA, or the software or the library they are using in demonstrating their attack. That library uses an optimization on the RSA, which is named as CRT, or Chinese remainder key. Okay. So basically what they do is that for implementing the decryption function, they separate the secret key D into two parts, same D. One DP and DQ. DP is like defined as D modulus P minus 1, and DQ is defined as D modulus Q minus 1. Now the thing here is like, I'm still trying to figure out this claim, but I'm not yet able to, but here's the thing. The claim is like, if you can figure out DP and DQ as an attacker, you can find out DP and DQ, you can construct the D. If you can construct the D, you can decrypt the message because N is known, C is given to you, encrypted message, and D, you have discovered it, or you have like reconstructed it after finding DP and DQ. Now the question comes like, how we can find DP and DQ? Now, to answer that, let's first talk about this one, that they have calculated the DP and DQ, what they do is that they first compute during the decryption, they compute two parts of the messages, MP and MQ. They separate the message, okay? So how the MP, the plain message or the decrypted message is calculated by C raised to power DP mod P, and MQ is equal to C raised to power DQ and mod Q. The thing is like, if I can get DP here and DQ here, I can reconstruct the D. Okay, now let me give you an example. How many minutes we have? How many of you have class after this? No one? Can I like go beyond 4:15? Okay. So, let me open the example. Yeah. So to calculate, let's say, and to calculate the MQ, what they are doing is C raised power DQ mod Q. So first they need to calculate this exponent, right? Let me just simply write that same statement here. MQ is equal to C raised to power DQ mod Q, right? But in actual implementation, this DQ is a huge number, which means that you need to do a lot of computation and it takes time for this part only. Only after that you can do the mod, right? So first you have to compute this one, but it is super slow. So what they have an algorithm which optimizes it, and they name it as scale, multiply, and modulo operation, a modulo exponentiation. So there what they do is they have these steps. So what they do is that they convert the data to the binary first. So can you see the screen? Okay. So here is the example. Now let's say you have to calculate the 3 raised to power 13. We are just replacing it with this one. C is 3, D raised to power Q is 13, just to keep it simple, right? So what they do is that first you convert 13 into the binary. So if you convert into the binary, it is, what is the binary? 1101. 1101. Okay. And after that, you apply that algorithm to reduce the time which is needed to calculate this part. Okay. And what you do is that you first set the result equal to 1. And this is least significant bit, let's say. This is most significant bit. You start scanning from the most significant bit, and then you do the operations depending upon the value of the bit. So first, whatever current result you have, you scale it. Okay, so 1 times 1. So this is scale step. Then you look at the value of the bit. If the value of the bit is 1, then you multiply it with the base. Okay, so 1 times 3. So you did the multiply. Okay, and after that, you take the modular separation with the Q of only this value. So for example, in the screen, they have 3 raised to power 13 mod 17. Okay, so 3 mod 17 is 3. So here you did scale, multiply, and modulus. Now then you go to the second bit, you do the same thing. You will now whatever, so that your current result becomes 3. So you repeat. So you scale it, it will become 9, right? Then you look at the second bit is 1. If it is 1, then you multiply it with the B. So when you will 9 times 3, it will become 27, right? And then you do the modular separation. The difference is like this step is same in every iteration. This step is same in every iteration. The difference comes from here, from multiply. So if the bit is 1, the bit that you are scanning, its value is 1, then you do the multiplication. If the bit is not 1, it is 0, then you don't do the multiplication, right? So basically what comes here is like, if you, let's say we will have 4 steps, right? 1, 2, 3, 4, 4 iterations. So in first step, you will have multiply. I'm not writing the remaining things, scale and modulus, okay? For the first bit. For the second bit, again, you will have multiply. For the second bit, no multiply. And for the last bit, you will have again multiply. Now, if as a spy, as a spy process, you can figure out, you can differentiate whether the multiply operation is performed or not performed, right? Let's say you don't have this one, but somehow you can figure out by looking at the memory accesses whether the multiply operation is performed or not performed. Then if it is performed, you map it to 1. If performed, 1. If not performed, 0. If performed, 1. What are you, and then you reconstruct. So this is like, this is the first operation, this is most significant bit, right? And this is least significant bit, right? When all the operation is done, you just put them in the order. You convert it into the binary, decimal. So it gives you what? Your exponent, which, if I go back to the slides, you can do the same thing. You can do the same procedure, or you can do the same steps by just observing whether multiplication was performed or not. You can set the bits to 1 or 0 and then put them together to construct DQ, right? Everyone with me? You can do the same thing. No, given that you know that victim is now calculating MP. If you know that victim is calculating MP and you have a way to figure out whether the multiplication is done or not done, you can construct also DP, right? If you are able to construct DP and DQ, the claim is you can construct based on their values, you can construct the D itself. So if you are able to construct the D itself, you can decrypt the message. Okay? Even if you don't cover it in your discussion lead tomorrow in the next lecture, it's fine. That how D is constructed from DP and DQ, but I will try to cover it after the discussion that how D is, or maybe before the discussion so that everyone is clear on that. Okay, any questions? Okay, now submit your reading notes.
Just a reminder.
No, not reading notes. Today is only class participation.
A reminder that I can't be here Thursday, but I'll bring you the form that I get from.
It's okay. I mean,
Well, I've asked for it, so.
okay. Okay, so one question, like the background which I'm giving, is it like helpful or like especially for the second day?
Very helpful.
Because when I was asking question and you didn't know what is inclusive cash, then I was wondering if you don't know, then how you are able to grasp the paper, because maybe it is not that much important, but the important in the sense that it is a weakness of the approach. Like if it is not inclusive cash, then I will not.
It helps like explain a lot of the terms and stuff that I see in the paper when I read through it beforehand. If I don't get them, you usually go over it
Okay.
here, so that helps a lot. And then I read it again before Thursday.
Good.